Chairman. My name is José Antonio García. This work is a work of one of my students, Dragos and Poiana, but I'm going to talk today about the stabilization of a dual optical frequency comb. In this case, for another application that is slightly different, the optical frequency comb is slightly different to the previous one because it's going to be done with electro-optical modulators instead of directly with the source, with the optical source. And the second difference is instead of analyzing the optical spectra for quasi-static phenomena such as the measurement for spectroscopy, I'm going to apply this measurement system to fast phenomena. That is, in this case, for the measurement with fiber Bragg gratings, but fast phenomena of vibrations and ultrasounds. So the parts of my presentation start with the motivation, three main points of the motivation and objectives. After that, I'm going to present a specific dual optical frequency comb, some measurements of vibrations and ultrasounds, and after that, what is a main part of the presentation, that is the stabilization and the stabilization of the dual optical frequency comb. After that, conclusions. Which is the motivation? The motivation is three parts, three steps of the motivation. First one is the application. Applications in this case are for vibration sensing and ultrasound sensing of fiber Bragg gratings with fiber Bragg gratings arrays. For example, here we can see two examples: the ballistic testing lab of our university, UC3M, and also the Legas gun of the facility at the University of Kent, in which we are measuring impact. We are measuring impact tests with fiber Bragg grating arrays. Another application is the detection of ultrasounds in this, with these sensors. Second motivation is the specific sensor. The sensor is a fiber Bragg grating. At last, a fiber Bragg grating is like a fiber optic strain gauge, where the Bragg wavelength is changing with a sensitivity of about 1 picometer per microstrain. And if we illuminate with a broadband source, the FEG, the reflective spectrum is going to be like this. We can observe it with an optical spectrum analyzer. Instead of using a continuous broadband source or a tunable laser, that is the other possibility, we're going to go to use advanced sources for fast interrogation of the fiber Bragg gratings. One is the optical frequency comb generator. An optical frequency comb generator is simply a number of tones that some of which can be within the spectrum reflected by the fiber Bragg grating. And the other idea is the use of the dual optical frequency comb for the direct readout of the wavelength changes into the frequency, changes in the frequency in the radio frequency domain. Thank you very much for your previous presentation, because the main ideas of this dual optical frequency comb were presented before. And which are the objectives? The first objective is to have a more efficient broadband source. In this case, we are going to sample only some points of the optical spectra with the optical frequency comb. We use a circulator illuminating the fiber Bragg grating, and the reflecting spectra is detected onto a photodetector. We use a dual optical frequency comb. We are going to map directly the optical spectrum into an RF or electronic frequencies. This is the way we are going to measure directly with optimized points in the spectrum and also with a direct readout onto the photodetector. The objective in this way is to include some tones of the optical frequency comb within the reflected spectrum of the fiber Bragg grating, and very small changes in the Bragg wavelength are going to be observed as amplitude modulation in this case, or phase modulation of these tones. Let's start with the dual optical frequency comb with electro-optic modulators. In this case, we use a coherent laser, a very stabilized laser, a DFD, that illuminates an electro-optic modulator that is modulated at frequencies of gigahertz and illuminates the fiber Bragg grating, and mean reflection is detected onto the photodetector. The idea is to select a number of tones and many of that within the fiber Bragg grating. Since we can change also, we can use different amplitudes for tuning the number of tones, and also we can use different frequencies in order to have the different separation between tones. We can, yes, exactly position the modes, the tones of the optical frequency comb within the spectra reflected by the fiber Bragg. The second part is the fast data readout by dual optical frequency comb. In this case, we use not only one optical frequency comb, but two. In this way, we have the mix of two combs in order to have a dual comb with a slightly different frequency, that is this delta F. This is in the order of megahertz, for example. An example, here we can see a typical comb just in the maximum sensitivity points of the reflected spectra of the FDG. If small changes are in the FDG, we can observe amplitude modulation in with counterphase, and here we can see the map of the optical spectrum in that 2 points with the electronic spectra with an electronic spectrum analyzer. The practical implementation is like this. Here we can see the acoustic modulator for a phase shift of the frequency, the two phase modulators, electro-optic modulators, and the couplers of the system. I want to remark that this is a portable dual optical frequency comb. In fact, it was working out of the lab. This is working in applications of aeronautical applications with Airbus. Some results, for example, with vibrations. This is a setup for applying vibrations onto the FDG. With in this case, for simulating impact tests, we apply some vibrations with a loudspeaker and observe the modulation of the two tones and the difference between them. In this case, it's remarkable that we were able to eliminate the common mode 3 dBs and to measure in the range of 18 microstrain with very high resolution. We went even faster. For example, with ultrasounds. In this case, we applied ultrasounds to an FDG at two frequencies, 40 kilohertz and 120 kilohertz, with a strain less than 1 microstrain measuring with this system. Here we can see slightly the results. Okay, but why we need a stabilization of this dual optical frequency comb? At last, if we want to change the frequency, we would like to change the wavelength of the laser in order to track exactly the center of the FDG, in order to measure only, in order to have a bias point of the wavelength and measure very fast and very small changes. So the idea here is to use, for example, a tunable laser, a simple tunable laser like the VCSEL. In this case, we change the wavelength, and the changes of the wavelength, even though didn't change the amplitude of each individual optical frequency comb, we can observe in the optical spectrum analyzer changes in the amplitude when we have dual optical frequency combs, because in detail, even though no significant changes in individual optical frequency combs, the interferometric nature of this setup is we have significant changes of the coherent output of the optical frequency comb. This is not useful if we have changes in in the wavelength in an unbalanced interferometer, this is not useful if the interferometer is going to change the length randomly. So we propose a stabilization of the system. We detect the output, and with some control of electrons, we're going to match to control the path length of the interferometer. We are going to control the optical phase in this case. Practical implementation is with a typical piezo-stretcher with fiber, with 73 turns of fiber, and the ability of compensate 22 p radians at the typical wavelength of operation, in this case 1.5 microns, and this is simply a handmade actuator. We can also use, for example, the acoustic modulator for compensating the system, but we tried with this actuator. Results. In fact, the practical characterization was done detecting onto the photodetector the typical dual comb, detecting onto the photodetector, and with simply detecting the main tone, the main mode, that is in this case is like a locking detection. We actuate onto the PCT in order to stabilize the dual comb. These are the results. We have the stabilized amplitude of the output of the dual comb with closed loop and with open loop in this case. And we can see here, for example, the effect of some vibrations onto the dual optical frequency comb. This is an example of the results of changing the two modes with no strain applied to the VG. Applying microstrain compression, we can one of the tones changes differentially two tones in amplitude and in traction in the other way. So we are going to detect that. In conclusion, optical frequency combs have been proposed as an optimized broadband source for fast FVG interrogation. The fast direct readout is going to be done with a dual optical frequency comb in this case, but the dual optical frequency comb has some instabilities. First one, because of the path changes in the interferometer, it's because of this setup, and the second one that if we have an unbalanced path, any change in the wavelength is going to change also is going to be observed as changes in the amplitude of the modes. So the proposed stabilization is with a PCT in this case. So we obtain a stabilization of the dual comb for direct measurements, and as future work, I want to remark that this implementation, compared, for example, with an acoustic with a compensation through the acoustic modulator, can be applied to other dual combs, for example, at wavelengths with infrared, different wavelengths that they use one. This is because the piezo-stretcher can be used in other wavelengths easily in this case. Thank you very much. Thank you for your attention.